Disproportionation reactions. So far we've been looking at redox reactions that involve atoms of one element being oxidized and the atoms of a different element being reduced. Occasionally some atoms are oxidized and some different atoms of the same element are reduced. Hopefully this is a clear definition of what disproportionation reactions are. I don't want you to come away from this thinking that an atom can be oxidized and reduced. If, for example, a disproportionation reaction involves, say, 10 grams of copper metal, there are many atoms of copper in 10 grams, some of which are oxidized, and some of the others are going to be reduced. One copper atom won't do both, just one or the other. You can easily spot a disproportionation reaction because the only non-hydrogen, non-oxygen atom or compound on one side of the equation appears twice on the other side. One being the product of reduction, the other being the product of oxidation. So in this equation we still write out two half reactions, only this time the reactant in both half reactions is the same. As before, we ignore the hydrogen-oxygen components of the equation, including them only if they're attached to the atom being oxidized or reduced. You might be wondering, how do we know if this is even a redox reaction? Well, this will be made clear when we discuss oxidation numbers later on. The rest of the steps in this question we treat as before. Balance the non-hydrogen, non-oxygen atoms first. In this case, the manganeses are balanced. Next, add water molecules to the side deficient in oxygen atoms, and hydrogen ions to the side deficient in hydrogen atoms. Add electrons to balance charges. If necessary, balance the electrons lost in the oxidation half reaction with the electrons gained in the reduction half reaction. In this case, we multiply the lower half reaction equation by 2. Finally, add the two equations, consolidating components that appear on both sides. In this equation, it looks like we have to deal with more than two different atoms in this redox reaction: the silver atom, the selenium atom, and the phosphorus atom. But on closer inspection, we see that the selenium trioxide ion is merely a spectator ion that appears on both sides of the equation, and should not be part of the net ionic equation anyway. In order to hide gold during the Second World War, Nobel Prize winner Niels Bohr dissolved the gold, stored it in a solution, and recovered it at the end of the war. A nitric acid and hydrochloric acid mixture called aqua regia is reacted with gold metal to form hydrogold chloride, a solution. While chlorine is an important part of this reaction, it doesn't contribute to the redox component of this reaction, because the chlorine ion that arises from the complete ionization of hydrochloric acid does not change, and is still a chlorine ion in the hydrogold chloride solution. It is thus a spectator ion, and again, not a part of the net ionic equation. For these or any other similar equations, balance the two main players first, and if a question in an exam demands that you include the spectator ion in the final balanced equation, then include the spectator ion in the half reactions. Like this. The first step doesn't change. You would balance the non-hydrogen and non-oxygen atoms as before, and then continue as before.